series and summation. So series does branch off of sequences. When the terms of a sequence are added, that's the key word there. When they're added together, that is going to result with an expression that is a series. So a series can be finite or infinite. So like our sequence before was 2, 4, 6, 8. So the only difference here now is that instead of just listing those terms, we're actually adding them together. So it's the same idea, whereas a finite series is just a couple of terms added together. An infinite series is the sum of a couple of terms, but it continues on. So it's not just a couple of terms, it's the list of and the sum of all of those terms continuing forever, whereas a finite, it's just the sum of a few of them. So for both series that they show you guys there, the index of summation is I and the lower limit of summation is 1. So the upper limit is 4 in the finite series and infinity in the infinite series. So what that means is this one here is telling you that that 4 is where we're stopping. We're only going to the 4th term, whereas this one is telling you we're going to continue. And that little letter there is just your Greek letter for sigma, and that just means summation, so that's summation notation. When it asks you guys to write the series using summation notation, so you're still finding the rule. It's just that now instead of just simply a sub n equals, instead of writing that, you're going to write the rule with a summation symbol next to it, essentially. You still have the process of finding the rule, though. So if we look at our sequence here, we've got 1 plus 8 plus 27 plus 64 plus ellipse ... to 729. So the reason this is a series is because the terms are added together. So we still need to figure out how we get from the term number to the term value. So again, 1 is your first term, 8 is your second, 27 is your third, 64 is your fourth. So what is the rule? How do we get from 1 to 1, 2 to 8, 3 to 27, 4 to 64? So in this case, it's just your term cubed. So I'm going to use the letter I. And again, summation notation, they don't have to be great. We're starting with the first term, and I'm going to write the rule. So it's my term value cubed, and that's my rule. There's no more to it than that. But we do have to figure out what term is this. Where is this series stopping? Because that's what we need up top there. So 729 is 9 cubed. So this series stops at 9. So it's going from the first term to the 9th term. And that is your series in summation notation. First term to 9th term with your rule. So if we look at the second one, how do we go from 1 to 1? 2 to 1/2, 3 to 1/4, 4 to 1/8. These are your term numbers. We use n, the term number, to get to the term value. So I'm looking at this, I sort of see that 1 times 1 is 1, and then 2 times 1 is 1/2, but 3 times 1 is not 4. So it only really works for the first two. So I also see that I could try to square 1 squared, but then 2 squared is 4, not 2. I do know that my top is staying the same, so I can at least say that we're starting at our first term, and I'm actually going to use n for this one. It doesn't really matter which variable you guys use. If you'll notice, 5 and 6 use k. You're starting at the first term, and I know that my numerator is going to consistently have 1. So if I'm looking at this, to get from 1 to 1, and 2 to 2, and 3 to 4, and 4 to 8, these are all multiples of 2. So what happens here, guys, is it's going to be 2 to the power of whatever your term number is minus 1. So for the first term, for instance, 1 minus 1 is 0. Anything to the 0 power is 1. For your second term, 2 minus 1 is 1. 2 to the first power is 2. For your third term, 3 minus 1 is 2. 2 squared is 4. You get 1 over 4. So the only difference is you have your rule, you're starting at the first term. In this series, because of the ellipse here, we don't have a stopping point for this series. We don't know where it ends. So this series continues on to infinity. We don't have a term where it stops. That's the only difference between number 3 and number 4. So when you're writing the rules for these guys, it's really just a matter of thinking about it a little bit, and it's sort of almost like problem solving. So for these, we like when it finds the rule for us. That means all we have to do is plug the values in. So when it asks us to find the sum of the series, we're starting, so if we look at number 5, we're starting at the third term. We're not starting with the first term. And we're going to 5. So starting at 5, or 3, stopping at the fifth term. So all we need to do is plug in 3, 4, and 5 for our k. And again, so if you notice, we've used n, we used k. Those are just variables. They don't have to be a certain letter by any means. So if it wants the sum of this series for number 5, all we're doing is plugging in the 3 values of that finite series that it wants, third through fifth term. So 3 times, instead of k, 3 squared minus 7. And I need to write this a little smaller. Hold on. So 3 times 3 squared minus 7. That's your first term. And again, this is a sum, remember, so plus. Okay, now we're going to plug in 3 or 4. 3 times 4 squared minus 7. That's your fourth term. Okay, and now the fifth term. So 3 times 5 squared minus 7. So 3 squared minus 7 is 20. 3 squared is 9 times 3 is 27. 27 minus 20. Or 27 minus 7 is 20. Okay, plus 3 times 4 squared minus 7 is 41. And 5 squared is 25 times 3 is 75. Minus 7 is 68. So then all you guys have to do is add up your 3 numbers and you get a total of 129. So to write this, you would write, okay, the sum of the series, 3k squared minus 7 from 3 to 5 is going to equal, let me write my rule here, 3k squared minus 7 is a total of 129. So we're just plugging those values in and finding the sum for all 3 terms. So go ahead and try the other one, and I'm going to move down to that key concept box. These special series, guys, are ones that are going to help you if they're asking for a really big series. So like from the first term to like the 32nd term. You don't want to sit there and plug in 1, 2, 3, 4, all the way up through 32. So if they're a certain type of rule, you can use these rules. So the first one is the summation from the first term to the nth term when your rule is just 1. So that's really not going to ever happen. It's just that means your series consists of just 1. 1 is n is 1. That's really all that's saying. The second rule is if you have, I'm just not good at writing these summation things. I try to get better at it, but if you have a series from the first term to the nth term, and it's just I. So that would be consecutive integers. 1, 2, 3. So that's what I'm saying. If they asked you to find the sum of the first through 100th term, you guys could sit there in your calculator and add 1 plus 2 plus 3 plus 4 plus 5 plus 6 all the way up to 100. But you don't need to. By plugging this in, or knowing this rule, it's just the nth term times n plus 1 over 2. So like if you were trying to find the sum of the first through 100th term, if n was 100, you would do 100 times 100 plus 1 divided by 2. So that's when you have consecutive integers. And then the last one, let me write that a little neater. Just for room's sake, is when you have a series of your terms squared. So, and starting with the first term. So again, if it's a large series that it wants with a lot of terms in it, it's easier if you guys know this rule. And that's just going to be whatever term you're going to times that term plus 1 times that term doubled plus 1 over 6. So if it's asking you to find the sum of I squared from 1 to 200, you don't want to sit there and add 1 squared plus 2 squared plus 4 squared plus 5 squared plus 6 squared plus 7 squared all the way up to 200. That's ridiculous. This rule will help you, and these rules, other rules will help you in these special cases.